Hello everyone and welcome to Easya.ae. Today we're going to explain experiment number 9 of Electromechanical Lab, which is squirrel-cage induction motor. The squirrel-cage is actually an AC input, three-phase balanced system. So the input is a three-phase AC voltage, and because we have three-phase AC input, we have three poles at the motor. Each one is connected to a phase of the voltage, and they are mechanically, that means they're actually 120 degrees apart, and electrically the voltage is also 120 degrees apart, which results in a rotating magnetic field, rotating flux phi. And this rotating flux phi induces a voltage inside the rotor. So now the rotor is not actually connected to any voltage, but we have an induced voltage because of the rotating magnetic field. So now we have a current carrying conductor inside a magnetic field, thus we have a rotation. And because of this rotation, we get speed and we get all the characteristics of a motor. Now this motor has different characteristics though, because it's not like the DC motor. We don't have anything connected to the rotor. So the speed in which it rotates is let's call it N, actual N. And the magnetic field rotates in NS. And NS is always greater than N, because NS only depends on the frequency. NS is equal to the frequency multiplied by 120 divided by the number of poles. So number of poles is constant. 120 is of course a constant. So it only depends on F. So no matter what we do, NS is going to remain constant. And the frequency we got here is 60. So we could have NS, and we have 3 poles. Sorry, we have actually 4 poles. Multiplied by the frequency, which is 60 Hertz. So if we have 60 Hertz, we're going to have 1800, and if we have 50 Hertz, we're going to have 1500. Now we're going to see what the relationship between NS and N. They created an easy variable actually to deal with that. They call it slip, and slip is the difference between NS over N. And if you want it in comparison to NS divided by NS, and they call it S. So that's the slip. And you can get the frequency, the torque, and everything in terms of slip. You can see that in the theory part of the course. We have one of the important things we have here is the relationship between the torque and speed. And as you can see here in this graph, as we increase the torque, the speed is going to gradually decrease until it reaches the breakdown torque, and then the speed will quickly reduce to 0. But in this experiment, we will not reach it. We will only reach here. This part will not be reached, will not be covered in the experiment, because in the lab the dynamometer provided does not provide that much torque, not enough torque to get the motor into the breakdown region. We also care about the power and the reactive and active power characteristics. We have P and Q. In the motor always draws reactive power, because you see here Q is the reactive power. The motor always draws reactive power because it needs it to create a rotating magnetic field. But P depends on the loading. See, when the motor has no load, the reactive power clearly exceeds the active power, because the Q is always, the motor always needs reactive power, but when there is no load, it only needs a little bit of active power. We're also going to see the characteristics of current versus the speed n, and we're going to see that on the computer part when we get the results, and we'll see the graph. Let's move on. Now we're going to connect the circuit. As you can see here, we have the three-phase voltage source AC, and of course, and we have our motor, our squirrel cage motor. We're going to connect the three phases to the three windings of the motor. We have three windings, a winding for each phase, and each of them is connected to a phase of the voltage, and we're going to short the other side and connect it to the neutral. Now here we want to measure phase voltage and line voltage and line current. So we're going to connect a voltmeter between these two lines. Let's call it E1, and another here, let's call it E2. So we have two measurements of the line voltage, and we want to measure the line current as well. So we'll take two measurements also. So we're gonna put a current meter in series. Have I1 here and I2. E1 and I1 and E2 and I2 together work as a watt meter to give me the line power. Now from circuits 2 course, we knew that to get the total power from the line measurements, we have to add PL1 plus PL2. We have to take two measurements of the line voltages and currents and get the power in the voltmeter in the metering application, as I will show you, and sum them up to get the total. Power. So the total is P total, and so is for Q1, of course, from the line measurements, plus Q2 line is going to be equal to Q total. In the experiment, we'll be seeing the graphs of the voltage versus the speed versus torque, and torque versus speed, and we're going to see the power P and Q versus speed as well. So let's move on to the practical part. Let's move on to the connection now. Now this is the three-phase voltage source, AC, of course. We're going to connect each phase to a winding. So this is phase 1, the first winding, phase 2, second winding, phase 3, to the next winding. And now we're going to short, as I said, the other side. And connect it to the neutral to obtain a Y connection. That's the neutral. Now we want to measure the line voltage, so we're going to connect meter 1 between two lines. So between the first line and the second line. And we're going to connect meter 2 between the second and the third. Meter 2 between the second and the third. And we also would like to measure the line current, so we're going to connect it in series here, the winding. So we got I1, and the same thing for I2. I'm going to connect it to the third phase just to follow up with the report manual, the diagram given in the report manual. That's it. Let's see now what are we going to see in the results.
And don't forget the prime mover.
Yeah, and don't forget to couple the prime mover and connect the speed and output torques, and most importantly, don't forget to connect the ground from the data acquisition unit to the dynamometer, and make sure the dynamometer is on dynamometer mode, not on prime mover mode, and that the mode here is manual, and you can choose to measure speed or voltage as we said in the previous experiments, and set the control knob fully counterclockwise, and let's see what we are required to do in the experiment. Now we're going to start the metering application. We have it already here. Don't forget to select the continuous refresh function. For our module here, we have to check that the speed is, especially for this version of the program, you have to check that the speed is labeled as, because it says at meter 7 and 8, torque and speed are at 7 and 8. You have to make sure that 7 and 8 are these things here. As you can see, torque 8,960 something. We have to make sure that the torque also is Newton meter and the speed is rotations per minute in order to get proper values of the measurement and to get the option of the corrected and not corrected function of the torque. Now we're going to choose the corrected function. Don't bother this one. We're required, the first requirement in the experiment is to get the direction of rotation. So we're going to start the motor slowly. Going to start the motor slowly in order to see the direction of rotation here. Just turn the power on. Just reduce the voltage. Don't forget to turn the voltage knob fully counterclockwise. Now let's increase the voltage slowly, and you can see this dot here shows the direction of rotation. So just increase the voltage, make it rotate slowly. As you can see here, it's clockwise, and that's the first requirement. Now the second requirement is to make the speed the same as the speed, make the voltage the same as the voltage mentioned here on the module. Here it's 380 because we're working with a 220 volt system.
Can you put your finger?
There it is, 380 volts. Okay. So we're gonna make the voltage measured by meter E1 380 volts. Let's go back to the metering. Now it's 145, and I make it 380. Make sure the load is fully counterclockwise, the load control knob. And 380 it is. Measure the speed. Now the speed is 1500. We're asked in the report if this is the same as it's almost the same as the theoretical speed. It is. The theoretical speed given at the rated condition is 1500 rotations per minute, so this is 1504, it's almost the same. Now we're required to increase the torque by a value that makes the mechanical power here measured under meters N and T. We have to make the mechanical power 175, which is the rated power. So
here's my question. We just adjust this one, huh?
Oh, I forgot. Okay, I will make it. I'll make it now.
It's okay, this one. So you will make this one 340?
180.
This is what's written there?
Yes.
Okay,
then
both they are the same?
Yeah, they are the same.
Okay.
We want to do the power thing, as I said.
This is the line voltage.
Yeah, this is the line. Because the phase voltage is 220.
Between two phases.
Yeah, exactly. Okay. Now we need to do something for the metering here, because we don't want, as I said, we want the total Q and the total P. To get that, we have to sum the values of P and Q, P1 and P2. So just click on the meter here and choose power, and choose PQS1 plus PQS2, and press OK. To do the same thing for the other meter, except that this one is going to be labeled as P down here. You can change it from P to Q, and this one is going to be Q. Now we want to, as I said, we want to increase the torque until the mechanical power is 175, as is the rated value. We're increasing the torque now. This is the mechanical power. This is the actual power delivered to the mechanical part. This is the mechanical power.
So as we increase
the mechanical power, yeah, because if you're gonna have harder tasks to do, so you need more power to do it.
Okay.
The total power increase when you increase the torque, but the mechanical power is the total power minus the electrical losses. Oh, we're not there yet. All right. Exceed it, controlling it through the voltage control knob. Once, yeah, it's almost there. You're not gonna get it precisely, but as close as possible. Okay. So we're supposed to measure the values of speed, voltage, and current I1. This is now the rated condition. Now we got the speed, we got the voltage, and we got the current. Just measure them as the rated values.
1,500, okay?
Yeah, it's 1,500 if there is no load. But now we have load.
Okay.
So we're done with this requirement. The second requirement is to start increasing the torque, the load torque, from 0 to 3 Newton meters, and take the values. I already did that. I got the data, so I increased. You can see the torque here. This is the not corrected function, just so you can see.
Increase what?
Increase the torque. I should start from 0.
Okay.
See, now I should decrease the torque. Start from 0. Now it's 0. So I should measure, add 0.3 Newton meters each time, and take about 10 measurements. So I did 12, so it doesn't matter. And take the graph. I already took the graph, but let's do it again with you guys. So we are required to get a lot of graphs here. The first graph is torque versus speed. So let's get speed in the x-axis and torque in the y-axis. This is speed versus speed. To get torque. Yeah, now that's torque. This is torque versus speed now. As you can see, it's non-linear. Let's see the one that we draw on the board on the theory part. So, which was speed versus torque. As you can see, it's the same, but we don't get that breakdown region. You see look at the minimum speed here. Look at the minimum speed. It's 962. It's not 0. We didn't see the breakdown region and the breakdown torque and stuff, because I told you we don't have enough torque to do that with the dynamometer we have, because the maximum torque we can get is 3 Newton meters. So we're not going to get that region in the graph. The second graph required, the third graph actually required, is the graph of Q and P versus the speed. So let's put speed here. And Y1, let's get Q. Remember that we did Q in meter 15. Yeah, it's the one we added Q1 and P1 and P2 in it. So let's choose that. And as you can see, when the speed increases, that's mean the load decreases. So when we have less load, we need less power. We need less active power. So let's see Q. What happens to Q? Q was in meter 16. It's also an addition of Q1 and Q2. And you see Q we always need Q, whether we have a lot of load, no load, rated load. It's not constant, but it doesn't change as much as P. You see here in the beginning, we call this almost, we have no load now in this position. Now P is less than Q, because we always need Q, but in the beginning we didn't need a lot of active power. But then we need when the load increased, the active power increased, and the reactive power increased, but didn't increase that much. You're also supposed to get the graph of the speed versus current versus speed. So line current, so we're gonna get on the x-axis, we're gonna get the speed. It's the same. So let's remove this one and get the current I1. All right. So you can see it's almost a linear relationship, and the current is decreasing as the speed increases. The last thing we're supposed to do in this experiment is get the direction of rotation when we reverse two of the phase connections. So let's see what happens when we do that. Let's turn off the power. Let's see what happens. I'm going to, these are my windings. I'm going to reverse two winding connections. Alright, I reversed it. So I'm going to start the motor really slowly to see the direction of rotation. Now, I'm going to turn the voltage control knob fully counterclockwise, turn on the power, increase slowly. So as you can see here, we're going counterclockwise, we're going backwards now, because we reversed the direction of rotation. Now we finished the experiment. Let's see you again in the next experiment.